Okay, so good. So last week we were talking about the Gibbs energy of the gas solution. Yeah. So in the beginning we were talking about just the mixing of the gas solution without any chemical reaction, and basically from those kinds of that example, the mixing of the gas example, we try to derive actually the mixing entropy. Because of the mixing entropy, because mixing entropy is positive, and so it's the entropy is increasing by the mixing of the two gas phases as one solution phase, and that actually increased the entropy and decreasing the Gibbs energy. So that's why naturally the gas always want to have the solution phase. Okay, and then I'll show you actually now once you have the chemical reaction, what kind of thing will happen inside of system. So when you have, before you mixing and after mixing, during the mixing, if you have the chemical reaction, the final state is really depending on your chemical reaction itself. Okay, there's the two ways to actually find out what's the final equilibrium state, and one of the very general way is to find the minimum Gibbs energy state, because the final state, thermodynamical equilibrium state, means minimum Gibbs energy state within the constraint of the mass balance. Okay, and so at the given temperature, we can just do the derivative of Gibbs energy with the composition at the temperature and constant pressure. Then when you get the minimum Gibbs energy, that's actually the state for you that's the equilibrium state. Okay, and in this case, you have to basically derive the Gibbs energy for the entire solution as a function of composition, and then make a derivative of that at the constant temperature and constant pressure. That's a very general way. Okay. And this can be applied in any cases. And now, if you're actually just using the very simple way, and one of the way to do it is using the equilibrium constant. Okay? So when you have chemical reaction, and if it's equilibrium state, it means whatever chemical reaction you can create inside of your system, whatever chemical equation you can put on in the given system, it should be always in equilibrium. So when it's equilibrium, the Gibbs energy of reactant and the product should be same. So delta G of reaction should be 0 at the given equilibrium state in the system. Okay? So we know the temperature, we know the total pressure, then we can actually calculate what would be the equilibrium state depending on basically it's depending on the chemical composition of your gas phases. And so when you have A plus B become AB gas phase, then you can say what is Gibbs energy of A and B and AB as a pure standard state. And when you have the Gibbs energy of reaction, so delta G of reaction equal to delta G naught of reaction plus RT ln the different partial pressure of the gas product and the reactant. So when you have the chemical reaction in equilibrium state, then delta G of reaction for any kind of the chemical reaction you set up should be 0. Okay, delta G of reaction is 0. Then this actually gives you the delta G naught of reaction equal to minus RT ln K, and K we call it equilibrium constant, which is expressed as the partial pressure of the product divided by partial pressure of the reactant with the stoichiometric number of the power for each partial pressure. Okay, that's how it is expressed. Okay, so now let's try to use those kinds of equation, those kind of concept to do the real actually the application for the apply that actually for the real application examples. Okay, so this is chapter 4 or chapter 5, sorry, of your homework exercise. Okay, so let's look at question number 1. So I think even the first one there's the mistake in the spelling. So oxidation, oxidation, oxidation of the nickel. So when we have the nickel solid and the nickel oxide solid are mixed in the gas atmosphere composed of the 15% of CO2 and 5% of CO gas, and then 80% of the nitrogen gas at 1000 degree Kelvin. And will the nickel be oxidized or nickel oxide become reduced back to the nickel metal? Okay, so that's the question. So we have the nickel oxygen reacting together become nickel oxide, and CO oxygen reaction together to CO2. So there's two chemical reaction Gibbs energy is given. Okay, So whenever you have seen this, whenever you see the now, thermodynamic problem, if there's any kind of chemical reaction, you have to think about two. So is this question asking you, okay, whether the chemical reaction going to the forward or backward? That's the one type of question. And the other type of question is, so okay, I'm in the final equilibrium state and find out what is the mixture inside of my final equilibrium state. There's only two ways you can ask. Mostly, there's only two things you are always asked. One, whether the reaction going to the forward or backward. So it tells you, okay, it asks you whether you are decreasing the Gibbs energy in this direction or whether you're decreasing Gibbs energy in this direction. So it's a transient period, transient state. Okay? So that's the one type of question. The other type is, I don't care about what happened in the middle. I'm in the final state. What will be my composition of the final state? What's my state? What's the chemical composition of each phase in the final state? There's only two types. Okay? Mostly two types, not only two types, but mostly these two is the two different categories you will always ask. Okay? So question number one. So I say, okay, I have nickel and the nickel oxide under the certain atmosphere, and it asks you, okay, whether nickel become nickel oxide or whether nickel oxide become nickel. So is this what? Is this final state? Or is it asking you what's the direction? It's a direction, yeah. It's a transient period. Direction. So when you see the direction, the easiest way to solve this kind of problem is, okay, so I set up the chemical reaction based on the available information, and I'm checking whether Gibbs energy is decreasing in this direction or not. Because thermodynamically, when you move to the equilibrium state, your Gibbs energy should decrease with that direction. Am I right? Is it okay? So that's the actual question here. That's what we have to calculate. So I have nickel, and I have the nickel oxide, and then my gas atmosphere is the 15% CO, CO2, and the 5% of CO, and then 80% of N2. Okay? Whether this will going this way, whether this will going this way. That's the question. Okay? And the two conditions we actually, two equations we have it is nickel I have this delta G naught of reaction 1, and I have this chemical reaction number 2 at 1000 degree Kelvin. Okay? Good. And this Gibbs energy is already given at 1000 degree Kelvin. That's good. Then, okay, so basically this one asking you this one. Is this one going this direction or going this direction? Okay? So if I know the Gibbs energy of oxygen, okay, and Gibbs energy of nickel and Gibbs energy of nickel oxide, then I can calculate delta G of reaction equal to delta G naught plus RT ln partial pressure or activity of the reactant or product. And whether delta G of reaction is going to become negative or positive. That's actually what we have to dictate here. That's what we have to calculate. Okay? And in order to do that, so okay, so nickel is pure nickel. Nickel oxide is pure nickel oxide. So the activity of each of this one is 1. So, okay. And in order to do that, I need a partial pressure of oxygen. Yeah? But unfortunately, I don't have partial pressure of oxygen directly. Okay? Because it's not given here. What's the partial pressure of oxygen? It's not given. Okay? And instead, I have CO2 and CO and 80% of the nitrogen gas. So, the second equation here, this will give you the partial pressure of oxygen. Because I have CO gas, I have CO2 gas. At the equilibrium between these two gas phase, I can calculate what would be my partial pressure of oxygen. Okay? That's the partial pressure of oxygen in the system right now. And when you actually enter this one, is this Gibbs energy, not Gibbs energy naught, G naught, delta G, which is delta G naught plus RT ln partial pressure. That term is going to be negative or positive. That's the question. Is it okay? When you have reaction, direction of reaction is depending on delta G, not delta G naught. Delta G naught is always constant at a given temperature. So you cannot change it depending on your condition. Yeah? Delta G is the important thing. Okay? So let's do, that's actually the 3 different ways. So let's start with the very first one. So let's do it. First case. So let's do step by step. So Ni, so for reaction 1, if I actually write down this one, delta G of reaction for the reaction 1 equal to delta G naught of reaction 1 plus RT ln my current activity and the partial pressure of the system. So this one, activity of NiO solid, and this product, reactant, activity of nickel solid, and partial pressure of O2. Okay, this is 1, and this is 1. So if I know this value, now I can say whether this is positive or negative, whether this entire delta G reaction is positive or negative. Is right? If that delta G of reaction, if this is negative, it means I'm having forward reaction. This is positive, backward reaction. If this is 0, now I'm equilibrium state. There's no chemical reaction happen anymore. Nickel and nickel oxide will stay together. That's what it means. Okay? So this is what we have to decide. This one, not this value. This value is constant. As you can see, this value is negative term, yeah? This is always, under this condition, at the given temperature, this is negative. That doesn't mean that this is negative. Yeah? This is depending on this value plus this value. Okay? So, I need this partial pressure of oxygen. And the partial pressure of oxygen, as I mentioned, is not given directly in the question here, in my system. This is determined by the gas phase, and the partial pressure of oxygen is determined by these two chemical reaction between these two gas phase, CO, CO2. Okay? So industrially, or in the laboratory, any kind of when you actually control the partial pressure of oxygen, the two most easiest way to control the partial pressure of oxygen is using the mixture of CO, CO2 gas or H2, H2O gas. Then by just equating them as a chemical reaction, we can find out what will be the partial pressure of oxygen at the given mixture of CO, CO2 or H2, H2O. Okay, it's the most easiest way to control the partial pressure of the system by using the gas mixture. Okay, so this one, now, from reaction 2, so this one, now, at equilibrium state, so at least CO2 will mix it in the gas phase, and it have its own partial pressure of oxygen. Okay? That partial pressure of oxygen is same as this partial pressure of oxygen in the system. Okay? So this phase, so because this is equilibrium state, delta G of reaction 2 equal to 0 here, because this is equilibrium state. So virtually how much partial pressure of oxygen is developed by the gas phase at the moment. So that's, and so it means we are assuming that gas is equilibrium state between the gas to gas. So this is delta G naught of reaction 2 plus RT ln now partial pressure of CO2 and CO and O2. So PCO okay, and I think there's actually one problem here actually. So if you want to calculate the PCO2, you need the mole fraction over the gas phase, or volume fraction over the gas phase. It's same in terms of gas, and total pressure. Okay, so this is mole fraction of CO2 plus total pressure, mole fraction of CO plus times total pressure, and mole fraction of O2 times total pressure. So total pressure cannot be actually eliminated by itself. So you need what's the total pressure. So P total. Let's assume it's 1 atm. Okay? So there's some missing information here. Okay? Then you can now calculate. Okay? So then this will be just the mole fraction of the CO2, so it's 0.15, and this is 0.05, and then you can get what's the partial pressure of CO2, O2 gas phase here now. Okay? And then you can enter this one here and then check whether this is going to the positive value, negative value, or 0. Depending on that, if this is the case, then it means the reaction going to the forward reaction, so that means nickel become nickel oxide. So all the nickel phase will be oxidized, become oxide. Nickel metal become nickel oxide. Oxidation happen. Yep. This one? Ah, yeah, of course. But we want to know whether this is going to the forward or backward. Yeah. I'm not talking about what's the final state. No. When you do this chemical reaction calculation, PO2 will be very, very small. 10 to the minus 5, 10 to the minus 6, for example. So it's not really changing the fraction that much. And of course, this, strictly speaking, this plus, there should be some O2 gas and all kinds of things, yeah? All this mixture should be 100%. Am I right? I mean, theoretically. So, theoretically, this cannot be like exactly like this, but I mean, this oxygen is very small, so it doesn't change actually the real ratio here. It more or less makes sense? So for example, let's put it in this way. So typically when you say, okay, air is 81% of the nitrogen, or 79% of nitrogen, 21% of oxygen. Yeah. But there's a lot of other gas phase inside here. You can have even NO, NO2, NOx phase, yeah? All this kind of thing. But this is basically like almost ppm level or below the ppm level, very, very small number. So it's there, but we don't care most of the time. But when you're actually doing some chemical, it's the same thing. So when you have CO, CO2 mixing together, typically the oxygen which is generating from this kind of the chemical reaction between CO, CO2 is very small, so we don't care in the most of the time. Overall composition of gas phase is CO and CO2. Okay? But however, theoretically, if you do the calculation, you can have very, very small amount of the O2. That's what we have to calculate first. Okay? So it wouldn't change the general composition of the gas phase. Okay? Is it okay? Is it okay? And then, I mean, because, so let's assume this way. So let's assume I have partial pressure of oxygen is calculated here, and if you add this one, this is less than 0, then it means chemical reaction going to the forward there. So it means I'm going to the forward reaction here. So nickel will absorb that oxygen and then become nickel oxide. Okay? And then the oxygen will be consumed, then more oxygen should be generated here. And then more oxygen can be generated by consuming the CO gas here. So this reaction going to be actually, so oxygen is consumed by the chemical reaction. Then you need more oxygen to continue this kind of chemical reaction. Then CO2 will be dissociated to the CO and O2. Okay? So the amount of CO2 will decrease with the time, and CO will increase with the time in reality. But I don't care what's the final state. I'm just asking you, okay, whether at the current state, is it going to this one or this one? That's the question here, yeah? Yeah. No. I'll show you later. So you're mixing two things. Yeah. Theoretically, yes, but it doesn't change. Yeah. So when we say pure solid, it's not solution phase. So nickel oxide is not the mixture of the nickel and oxygen as a chemical solution. So if nickel oxide is solid solution, then it means nickel can have 1% of oxygen solubility, 2% of oxygen solubility, and then it goes to the 50% of oxygen solubility. So it's all the way through. It is not there. So pure nickel, and then there's nothing in the middle, and then you have nickel oxide, and there's nothing, and then become oxygen. Yeah? Is it okay? So then, it's a stoichiometric amount of the element is existing to make this phase. It's not solution. If it is solution, you can have different stoichiometry in the same solution. Okay? That's pure solid phase. It's not pure means, pure doesn't mean that in this case, one element, pure, 100% purity, one element phase. It's a solid phase, pure solid phase, and solution phase. Or theoretically, you can even say that, okay, stoichiometric solid phase, that's the pure solid phase, activity equal to 1. So when you have certain ratio of the atomic mixture can only generate that phase. That's I call it pure phase, pure solid phase, or stoichiometric solid phase. Is it okay? Do you understand? So for example, Fe nickel solid solution. This is solid solution, yeah. But when you have the pure iron, it's still pure, yeah. Pure nickel, it's still pure. But Fe 0.5, nickel 0.5, this doesn't mean that this activity equal to 1, because nickel and iron ratio can be changed from 0 to 1. Then it's a solid solution. Then we have to consider Gibbs energy of solution phase, not Gibbs energy of the pure stoichiometric phase. Okay? You good? Okay? Or more in general, when you find out that this Gibbs energy in the book as a table, then mostly this is the stoichiometric phase. Okay? So how about let's try to really calculate what's the partial pressure here. Okay? Then we'll see what's the number, and then we can get reasonable the idea. So let's go back again. So we have this condition. So basically, right now we have the two separate, yeah? I have gas phase, I have solid phase. Okay? I mix it together. And now I start I allow them to make a chemical reaction. Then you can get the more oxygen, or you can produce the oxygen, yeah, from the chemical reaction. Is it okay? So I'm in the beginning of that chemical reaction, and then I want to know whether this reaction going to this way or that way. That's my question. Is it okay? So inside of gas phase, they're already in the equilibrium state, and now I'm just having these two on top and just adding into the system and see whether this is going to this one or the other way around. Okay? So the second one here. So at those gas conditions, at least we know what would be the virtual oxygen pressure, because it's too small, so it's not written there. And so let's try to calculate that partial pressure of oxygen here. So delta G naught 2 equal to minus 195700. So for example, this one, So this one. Okay, and this is minus 1, 9, 5, 7, 0, 0, minus 1,000. Is it okay? If P total. Okay, good. So, as you mentioned, theoretically, if you want to do the very, very correct calculation, instead of 0.15, we have to say that, okay, 0.15 minus x, 0.05 plus x, and then 0.5x to make actual mass balance. That's necessary, but eventually when you do it, that actually x is very, very small, so it's become negative. I mean, it doesn't actually matter here or here. So it's only actually the matter of this one. Okay? So then, so this one is 0.15, 0.05, x02 equal to minus exponential 1,95700. Okay, and P of x02 equal to B. Eventually, so this one go there, so this will be 3 times. So this one going this way minus, so it's from plus exponential. Is it correct? Square. If I move this one there, plus, minus, 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 yeah. Oh yeah, so this is plus here. No, minus, minus, oh yeah, okay. There's no exponential here, yeah. This is good. And then now if I have x squared, okay, so this one, this, exponential this one, so it's minus. Is it okay? Is it good? I think you are better than me in terms of mathematics now. Is it okay? It makes sense? So I move this one back, and then I move this one. So this one going to the denominator first, and then I just switch. So and then I want to just make it multiplication. So I just make it minus, and so it looks like this, yeah. And then if you do that, so x02 mole fraction will be. Anyone who have the calculator? So do we have Excel file here? Excel. Okay. So, not complayer. Anyone have the calculator? This will be, okay, 3 times exponential minus 1,95700 divided by square. So 3.2, 10 to the minus 20, yeah? and mole fraction. So if this is 1 atm, so partial pressure of oxygen is this value. Yeah? So it's very, very, very small. So that's why even it is generated here, it doesn't change anything for this CO and CO2. Is it okay? Typically, I mean, this is the case. CO, CO2, H2, H2O. It actually generates very, very small amount of oxygen. So you can, most of the time you can neglect it in the mass balance calculation. Okay? So when you have this one, now you can enter this one into this equation here. So then this delta G not 1 become delta G now 1 so delta G not 1 was minus 148350 plus this value RT ln partial pressure, so PO2. So is it okay? So instead of plus, I just make it minus because I just changed the swapping actually the numerator and denominator, numerator and denominator. So this will give you that's 148350. Then I'm gonna have this one minus so this will be positive term, yeah? So this will be 22,479. Is it right? Wow, I didn't make something. Ah, so 0.5. That's too big number, so okay, 38. Three, 8, 216. Okay? So, delta G of reaction 1 is positive. Okay? So this is this case, so it means reaction going to the backward. Is it okay? Very standard question you're going to see in your midterm, number 1. Okay? So it means now it's going to this way. So it means nickel oxide is not producing. So nickel oxide will be reduced to the nickel metal. Is it okay? This is the first, one of the first way we can actually do this calculation. So now, how about second way? We just combine the reaction 1 and 2. Then it's much simpler. Okay? Okay? The simplest way. Now even we don't have to worry about the CO, CO2, like a recombination or whatever, because O2 will be just eliminated here. So then nickel plus CO2, nickel oxide plus CO. The chemical reaction Gibbs energy is delta G naught 1 minus delta G naught 2. Is it okay? You good? So, same thing. Because I have to know whether this chemical reaction going to the forward or backward here. I'm not talking about equilibrium state here. I didn't ask you equilibrium state. I'm asking you whether the reaction going to the forward or backward. So what I have to calculate is delta G of reaction. This is delta G naught of reaction plus so nickel oxide is okay. This is what I am to calculate. This is 1. Under this condition, even you don't have to worry about partial pressure or total pressure, yeah? Because I mean, it's just eliminated here by itself. This is 0.05, 0.15. Am I right? That was condition? Yeah. Okay? And then, if you do this calculation, so let's look back here. So delta G1 minus G2 was minus 14A350 plus 195700 plus RT. So this will be 0.15 divided by 0.05. Or 0.05 divided by 0.15. And then if you do this one, this is positive again, yeah? This is 38216. So it's the same value as the first one actually. Because we just replace this CO2 by PO2. So it should be same. It's same chemical reaction we are doing. So two separate way or combined as one equation and to one shot. Okay? So that means the reaction going to the backward reaction. So backward reaction is moving this way, yeah? So nickel will be produced from the nickel oxide. Is that okay? So this is second way. The third way. Third way. So third way is looking at actually the partial pressure of oxygen itself. Okay? So we're just talking about two different systems. So I have a gas phase which produces partial pressure of oxygen, and I have a nickel oxide will produce also partial pressure of oxygen at the equilibrium state. So for example, this is, let's assume this is PO2, partial pressure of oxygen. Okay, so until certain time, until certain value, you have the nickel will be stable phase. Above that, you'll have nickel oxide will be stable phase. Because I have a metallic phase, if I give oxygen little bit by little bit, then nickel will react with oxygen, start to producing nickel oxide. Okay, and this is same thing when you actually look at iron ore reduction. So I have FeO. And then if I take out oxygen, at certain point it becomes pure iron. So depending on the partial pressure, it's not like taking out continuously. At certain point it's suddenly changing to the other one. Okay? So that's reaction, oxidation and the reduction process. Okay? So when you have, so if I put metal is under the oxygen rich environment, it becomes oxide. Okay, if your oxide is almost zero oxygen condition, it loses all the oxygen, it becomes metal. There should be the equilibrium partial pressure of oxygen. So-called this one is PO2, equilibrium state for nickel and nickel oxide. Okay, so this is basically virtual system between the nickel and nickel oxide. Okay, and now I have my gas phase. So this is now PO2 of the gas phase. So it's controlled by CO2 ratio. So this is actual partial pressure of oxygen in the system by the gas phase. Okay, so this one with this calculation here, CO2 all the equilibrium by using chemical reaction 2, this is 3.2 10 to the minus 20. So under my current state, I have 3.2 10 to the minus 20 ATM. So this is my current partial pressure of oxygen produced by CO2 mixture. And nitrogen is diluting the system, yeah? It's nothing special. So this is my current actual partial pressure. And I'm comparing this one with my equilibrium, virtual equilibrium partial pressure between nickel and nickel oxide. If this is higher than this value, then I'm here, yeah? So it means nickel oxide will be produced. If this is lower than this value, I'm here, then nickel will be produced. Do you understand this? Okay. So in order to do that, so we know this value, now we have to calculate this value. So this value, it means, okay, I don't care about other environment. I have only nickel and nickel oxide. What would be my equilibrium partial pressure of oxygen? Then I'm using just reaction 1 only. So according to the reaction 1, so equilibrium partial pressure at between nickel and nickel oxide. So we are talking about this one. So I assume nickel and nickel oxide is in equilibrium state. What will be my virtual partial pressure of oxygen at that condition? Okay. So then it means delta G, reaction 1, should be 0. So delta G of reaction 1 equal to delta G naught eventually you will get only this value here. Because activity of nickel and nickel oxide is 1 because we are assuming that this is pure stoichiometric phase. So activity equal to 1. Eventually you will get this one. And I'm assuming this is 0 to get this equilibrium partial pressure and virtual equilibrium partial pressure for nickel and nickel oxide. So then PO2 will be exponential minus delta G naught 1 of RT square over entire thing square, yeah? Okay? Is this okay? Okay, let's try to calculate this value. So delta G1, this will be exponential minus minus, so it should become plus. So this will be 148,350 of am I right? So the exponential minus delta G naught 1 over RT. So something wrong. What's wrong? So if I just flip it, so minus minus, so it's plus here. Sorry. Because this is going to the other side, it's minus, and then I'm flipping, so it's minus minus, so it's plus here. I'm sorry about it. So this will be this value, Then I have to this one multiply by 2 square. So 10 to the minus 16. So 3.17, 10 to the minus 16. Okay? Okay, so this is at this temperature, 3.17, 16 atm. This is minus 20 atm. So if you look at this one, so my virtual partial pressure for nickel and nickel oxide equilibrium state is, can be made by partial pressure over 3.17, 10 to the minus 16 atm. Okay, but my actual partial pressure is lower than that. So I should have nickel instead of nickel oxide. So this should be reduced to this one, yeah? Okay, so this is another way you can look at this problem. Okay, so depending on the case by case, you have to use one of this approach. Okay. You good? Good? Coke. What's his name? Hey, with the hood. Are you okay? Are you okay? You understand? There's 3 ways to solve this problem. You have to know this one. I'm telling you, if you don't know this one, you'll have serious problem in your midterm number 1. 50%. If you don't understand this one, I guarantee you cannot get less. You can get less than 50% for your midterm number 1. Okay, this is the basic, and now we're going to add up on top of this one. Okay. Yeah.
Suddenly it's a bit confusing that in the second solution, the value of partial pressure CO2 and CO is 0.215 and 0.05.
Yeah.
Which is exactly same as the initial state.
Yeah.
You wrote that way just because the values really change during the reaction is really extremely small, right?
Yeah. Yeah. So basically, okay, just think about it. So I'm not asking you what's the final state, yeah? I'm just the beginning. So in the beginning, I should maintain same value, yeah? So now I have 15% of CO2 and 5% of CO in the gas phase, okay? Just beginning, okay? And then I'm adding nickel and nickel oxide inside of that gas phase. And then I'm asking whether this is going to this way or this way. So I haven't changed my CO-CO2 ratio yet. So this is my current state, okay? According to my current state, is my chemical reaction going this way or this way? Is okay? So of course you have to enter initial value, yeah? I'm not talking about final state. I'm still in the initial state. I'm just looking at, okay, I'm going to this way or I'm going to this way. Okay? With moving, you are going to change your composition. Then you have to, at each state, you have to check again whether you are moving forward more or not, yeah? And then at certain point, if you cannot move anymore, if it becomes 0, basically, then you stop. Okay? I'm not asking you what's that final stop. I'm just asking you, when you're actually starting from this one, is it going to this way or this way? Okay? So when you look at the actual question, you have to be very careful. What is exactly asked by the actual question, okay? Am I looking for the final state, or am I looking just at that state, looking for the direction, or I really want to calculate final equilibrium state? This is in the middle of the process. I'm basically asking you, am I going to left side or right side? Direction. Okay? Good. this is in fact actually difficulty in the thermodynamics. So when you guys doing your homework and when you guys doing your midterm and final, I have to check all your actually step because there's many different ways to solve the same problem, okay? And sometimes you simply make a very, very interesting approach too, which I haven't imagined before, and I'm very happy to see those kinds of the imaginary actually solution too, okay? Okay, good? So you don't have to always stick with this one. If you have your own standard, you can just go with that. I'm fine. As long as you feel like this is the correct step, I mean, it's okay. There's no real one solution. Okay? There's many different pathways to calculate. Same question. Okay. Number 2. So we are suggested to make a bearing made of the small MO2Si3 particle in the copper matrix. So molybdenum sulfide MO2S3 is inside of the copper matrix, and will this MO2S3 will have chemical reaction with the copper and then reduce to the other actual sulfide or not at this 727 degrees Celsius at 1000 degree Kelvin basically, yeah? And assume that copper sulfide, molybdenum, copper solid Cu, and the molybdenum MO, and the Cu2S, MO2S3, all of them is insoluble each other. It means all of them stay as a pure stoichiometric phase. So it means activity of all these four, this form, it's 1. That's what actually insoluble means. So when you make a solution soluble each other, then the activity cannot be 1 sometimes. But in this case, there's no solubility in each other, so it means it stays as it is. If it's forming, it just stay as a stoichiometric phase. Okay, so if you look at chemical reaction here, okay, MO2S3, if it is reduced, it becomes MO, yeah? There's no other MO sulfide, yeah? And then when you actually reduce this one, then sulfur should go somewhere, and it should react with the copper to make a copper sulfide, basically, okay? Just think about it. Is this asking you final equilibrium state, or is this asking you direction of the reaction? What do you have to calculate? So I have initial state, and I'm asking you whether this is reduced or not reduced. What's that mean? Is it asking you direction, or is it asking you final state? It's a direction, yeah? So that means somehow we have to calculate delta G of reaction, yeah? Not delta G not of reaction, okay? So I have system here. I have copper, okay, and these two, okay? I'm having reaction. And one possibility is, so Cu and MO, it can form Cu2S. So this is what it's asking basically. Is this possible or not possible? Okay, so Cu is the, how much it is? Cu is Cu2S, so I need 2 moles. Well, let's do it in this way. So this one, I have 1, so this will be 3. This 2, 6. Does this make sense? So if there's chemical reaction, I mean copper, if this is sulfide, so Cu2S, and if this is reduced, this is MO here. So if you consider this possibility, then we can set up the chemical reaction like this. Okay, so it's the copper and the MO2S3 it can react together CO2S and MO or not. And this is solid phase. And this is solid phase, and solid phase. All equilibrium solid phase. And delta G of reaction. Okay? Good? So, if you just set up this one, let's think about this way. Okay. So I want to know whether this, not delta G not, I want to know delta G of reaction, whether it's positive or negative. That's direction, yeah? That tell you what's the direction of reaction. Okay. So delta G of reaction, delta G not of reaction, plus RT ln, in this case, activity of each. And all this activity, in this case, equal to 1, yeah? Because all of this is pure solid stoichiometric phase. There's no solution phase. So all this one is 1, 1, 1, 1. So in this condition, this one is same. Okay? So in order to calculate whether this is going to the forward or backward, basically the only information we need is this one, delta G not of reaction. Okay? So now let's look at it. Okay, Cu2S and Cu plus S2. So I have that delta G naught, which is given at the temperature, yeah? So first reaction, so I have this Cu2 and second one, I have MO2 so basically I have to combine what? This minus 3 and plus 1. Then S2 gas phase will be eliminated here. Gas phase. So this will be 6 Cu okay? So if I know what's the delta G naught of this reaction, so this one minus 3 times of the delta G naught of 1 times, or 1 times okay, so you can get it. And this is basically this one, yeah? This is simple. Okay, so this is most simplest way to approach this one. And the other way is, so we can have a secondary way too. So at 1000 degree Kelvin, so it's Kelvin, yeah? 727 degrees Celsius, 1000 degree Kelvin. So this one, if this happening, what will be my partial pressure of S2? Okay, and then when this is happening, what will be my partial pressure of S2? You can compare these two together too. Okay, and then you can think about, okay, is it really make sense? I mean, going to the forward or backward? But this is most simplest way. Okay. Now, I mean, the other way I can actually generate this question, little bit more complex, is like this. Okay. I have S2 gas phase. Then, under that S2 gas phase, is this stable or not stable? the same question as I showed you before, yeah? It's like question number 1 in this case. Okay, if I have gas phase and that gas phase produces S2 partial pressure, under this partial pressure condition, is this will be stay as it is or is it going to change it? Okay? Well, S2 gas phase can be generated SO2 and SO pressure, or SO2 and then O2 pressure. I can control the S2 gas phase, yeah? S2 plus O2 become SO2, yeah? So I can control this partial pressure by this one, or I can even control this way. I can multiply actually the difficulty of this problem very easily in this way, yeah? Okay? The concept is delta G, is this negative or positive? That's in the end what I want to actually see it here. Yep.
For the first reaction, the enthalpy and entropy term would be...
Doesn't matter, because I just give you the total Gibbs energy already. What's the delta G?
If we were to define
You have to use the Gibbs-DM relationship. Gibbs-Helmholtz relationship. So when you have DH, so when you have delta G of reaction and as a function of temperature, if you make delta G of the T with the 1 of the T derivative, then you can have delta H here. And once you know the delta H, you can calculate delta S. Okay? It's not A plus BT, so it's a little bit more complex. But I mean, you can calculate it if you like. Okay? Good? Okay, let's look at question number 3. So calculate the partial pressure of O2 at 1000 Kelvin in the atmosphere of H2 and the H2O gas, and pH2 ratio is 6.0 times 10 to the minus 3. And under this condition, so first calculate partial pressure of O2 under that condition, and then under this condition, will the nickel oxide can reduce to the nickel metal or not? So there's 2 questions here. Is it okay? This is almost exactly same question as the question number 1. Yeah? Question number 1, I didn't ask you to calculate partial pressure of oxygen. Okay? And just calculate whether nickel and nickel oxide, which one is existing. Yeah? So, even without doing really any calculation, so let's just look at, okay, so how to calculate PO2? So, if you look at the first chemical reaction, H2 gas plus O2 become H2O gas, and we have delta G naught of reaction is given at the given temperature. Okay, temperature is 1000 Kelvin. So if you enter T equal to 1000, you can get what's delta G naught of this chemical reaction. At equilibrium state, for this gas phase between the H2 H2O, delta G of reaction equal to 0. So delta G naught of that chemical reaction equal to minus RT ln partial pressure of H2 over partial pressure of partial pressure of H2O over partial pressure of H2 and PO2 in root. Okay? And you know H2O ratio 6.0 10 to the minus 3. So if you enter that, the only missing variable is PO2. So you can get the PO2. It's very simple mathematics, yeah? And then once you know that PO2, now for the second one, nickel plus oxygen become nickel oxide. Equilibrium constant. So equilibrium constant means at the equilibrium condition, so it means delta G equal to 0 and delta G naught equal to minus RT ln K. That's the K, yeah? Equilibrium constant. So from this one, you can back calculate what's the delta G naught of reaction if you like. Or under that condition, equilibrium constant means activity of nickel oxide divided by activity of nickel divided by partial pressure of O2 in root. That's what it means here. Equilibrium constant. Understand? So, question number 2. Equilibrium constant is activity of nickel oxide, activity of nickel, PO2. So this is what it means here. That's equilibrium constant for that chemical reaction. Okay? At this condition, and this is given like 10 to the what? 5.6, 10 to the 7. This is 1, this is 1. Then I can calculate what's the partial pressure of oxygen to make the nickel and nickel oxide in equilibrium state. Okay? That's the one I actually showed the kind of there's the virtual partial pressure of the nickel oxide in equilibrium state here. So that's the value you can get here, PO2. This is virtual oxygen pressure, partial pressure, which make this chemical reaction in equilibrium. So this chemical reaction we are talking about is nickel and nickel oxide. So when nickel start to make a reaction with oxygen at equilibrium state, nickel and nickel oxide existing together, that's equilibrium state, yeah? Because reactant and product should be exist together at equilibrium state. Under that condition, what would be the virtual partial pressure of oxygen? That's this value. Okay? If you do this calculation, I don't know, this looks like 10 to the minus 7 reverse, so it's about, something, 10 to the minus 8 or whatever, ATM, or square, so it's 10 to the minus 8, about 10 to the minus, about that value, 16. So you have to calculate very carefully. And then you have to compare these two values. So it's the actual partial pressure of oxygen by the gas, H2H2O. If this is higher than your virtual partial pressure of O2 or not. If this is higher, the actual gas pressure is higher than your equilibrium virtual partial pressure, then you're going to have oxidation. So nickel oxide will be stable. If this is lower than your virtual one, then you'll have reduction. So nickel oxide become nickel metal. Okay? That's what I show you as number 3, the third possible way to calculate question number 1. Okay? Or if you don't like it, as I mentioned, from delta, so equilibrium constant, you can calculate what's the delta G naught of reaction, and then you can combine first and second reaction together. You can just eliminate the oxygen potential, for example, and get oxygen partial pressure and get only H2H2O and NiNiO reaction. And it going back to the the second step, I actually show you the second way I show you in the question number 1. Okay? That's another way. Okay? Am I doing too fast? Everyone okay? Is it too fast? Okay? Too slow? Too slow? Too generous, yeah? Okay, now question number 4 and 5 is your homework, so I'll just skip it. 7, 10, this is also your homework. 16 is also your homework. Okay, question number 8, sorry. Because every year I'm actually changing the question for your homework. So question number 8. Okay. So we have 1 mole of CO gas and 1 mole of H2O gas in the sealed container. Okay. And the system, now the container, is heated up to 1500 degree Kelvin. When the equilibrium is reached at the 1500 degree Kelvin, what are the mole fraction of CO, H2, and CO2 and H2 in the gas phase? And what is the partial pressure of O2 in the gas phase as well? So now it's a little bit complex. Okay? The question is completely different. In the previous questions, it was asking you, okay, whether I'm moving forward or backward. It's a direction of reaction. And this one, if you look at it, so I have 1 mole of H2O and 1 mole of CO, and then I allow them to have chemical reaction at 1500 degree Kelvin, and the final state, what is my chemical composition? What's my composition of each gas phase? So it is not asking you anymore, what's the direction? I know the final answer already. I know the direction. I know this will react and produce this thing. At that condition, what is my final gas composition? Yeah, it's different, yeah? It's not asking anymore direction of chemical reaction. It asks you now, what's the final state? Okay? So it's different. What's the chemical composition of your final state? Okay? So for this one, now you have to change your style of the calculation. It's not anymore asking you whether delta G is going to the negative or positive. Now we assume that delta G equal to 0, equilibrium state. And then under this condition, what would be my chemical composition? Is it okay? 5 minutes more. Is it okay? 5 more minutes. So initial state, I have 1 mole of CO, 1 mole of H2O. And I know this one will be now CO, CO2, H2, H2O. And then actually there's oxygen too. But oxygen amount is so small, in the beginning we'll just assume that there's nothing. This is assumption, but when you actually do all the calculation, if this assumption is not not satisfied, then you have to do another calculation. But let's start with this way. So this will make this 4. Okay. So now we have mass balance problem. Okay. I have initial, my final. So as you see, 2 CO. This is delta G naught 1, delta G naught 2. Okay, so CO becomes CO2. CO becomes CO2. During that, CO becomes CO2. H2 becomes H2O. Okay, so if you just combine together, then 2 moles of CO will produce plus H2O. Okay, so I have this chemical equilibrium in this system. So CO will react with H2O. CO react with H2O, produce CO2 and H2. Okay. However, it's not going to be 100% this one because at equilibrium state, delta G of reaction equal to delta G naught of reaction plus RT ln this partial pressure of CO2 square, partial pressure of H2 square, partial pressure of CO square, partial pressure of H2O square. So this is not 1, so my delta G is, my delta G at equilibrium state, this is 0, then delta G not equal to this value. And this is basically with the total pressure, but it eliminates each other because total pressure square, total pressure square, total pressure, eventually it just gives you the mole fraction of each phase, yeah? So delta G naught of this reaction equal to minus RT ln mole fraction of CO2, mole fraction of H2, mole fraction of CO, mole fraction of H2O. Is it okay? Yes, all the gases have the square, so I just take out that square term in front of the ln. Okay? So now, okay, we have one equation, and then 4 variables, 1, 2, 3, 4 variables. Okay? So let's look at how, so if, with 4 variables with one equation, it's impossible to solve here. So we need at least 4 variables with 4 equations. Okay? So if I have this is 1, and let's assume I'm start to producing CO2 gas. So 1 mole of CO2 will produce 1 mole of CO. So if I have X mole of CO2 is dissociate to the oxygen and the CO, it will produce X mole of O2, yeah? So now we do this one. So CO, so when you have this kind of thing, typically we do this one. CO, CO2, H2, H2O, okay? So I have initial condition and the final condition. So final is, means equilibrium state, yeah? Initially, I have 1 mole of this one, CO 0, 0, 1 mole, okay? Let's assume I am actually losing X mole of CO, then this will be X mole, and this is 1 minus Y, and this is Y. Because it doesn't have to be exactly the same. But if you look at this one, okay, so between this H2O and H2, so this one is related to this chemical reaction here. So X and Y should be eventually same, luckily or unluckily. Yeah. This one producing this one. So the X and the Y should be same. Is it true or not? Can you say or not? So is this X and the Y should be same or not? Mathematically, same? I don't think it is same. Anyone? It should be same? It makes sense? This produces this one. During that, it will produce 1 mole of oxygen. And that 1 mole of oxygen should react with this one to produce this one. Does it make sense? It's a very tricky question. Because if this is not 0, then you cannot say in this way, yeah? If this is 0, yes, X and Y is same value. If it's not, you cannot say in this way. Okay? So, in fact, I mean, if I add oxygen here, I'll have oxygen will be the function of X plus Y here too. It's a little bit tricky, isn't it? So, let's assume at least, I mean, in the beginning, it's different. Then let's look at how many actual variables we have. So now, okay, so under this equilibrium condition, if I add this xy here, so this will be 2 variables with 1 equation. Am I right? Because this mass balance will go inside 2 variables with 1 equation. Yeah? Well, if you assume that, yes. If it's not, then now it's a very big question, yeah? So, can we solve this one or not then? So, before that, let's look at another one. The total number of moles of the gas phase. If you look at it here, is 2. And total number, so typically you have to add also this one to make sure that you are not missing any additional actual information here. Total. 2, 2. Is okay? 2 moles and 2 moles. So when you say PV equal to nRT, the pressure is not changing. The volume is constant and the total mole of the gas phase is same, then temperature is same. So there's no change of the pressure, at least. Total pressure is same. Okay? So, if you actually solve this problem, you have to now make an assumption. There's no other way. Assumption number 1, as I mentioned, O2, let's assume that this is almost 0. Okay? Because that's the only way we can actually solve this. Then xy same as y. Okay? And then if I enter this one now, delta G naught of reaction equal to minus RT my xCO2 is x, and then H2, yeah, this is x again, x and y is same, and then this is 1 minus x, then square. Okay, so we have one variable with one equation, and then you solve this one and see what's the x value, and then once you have that x value, now you have to prove that whether your assumption here is okay or not, yeah? So the only way you can actually check is whether this oxygen is very small number or not. Okay, so once you do this one and find x value, and then you assume that x and y is same, then by using this chemical reaction, one of these chemical reaction, delta G naught or delta G naught 2, so delta G not equal to, for example, minus RT ln this PCO2, okay, PCO square and PO2. And then you have to enter again, same actually the pressure here, and then calculate what's the partial pressure of O2. Okay? And then see whether this is very small or not. If this is not very negligibly small, this assumption is wrong. This is negligibly small, you can say that, okay, safely, this is okay. Okay? Now, there's actually this total pressure is equal to 1. You need the total pressure, otherwise you cannot calculate it. So total pressure should be 1, because this cannot be eliminated each other. Yeah? There's P total will remain. So partial pressure of CO2 will be some partial pressure. It's not total pressure. Yeah. Yeah. Should be same, exactly same. Yeah. Whether you enter to this one, final condition equal to first equation or second equation, it should be exactly same. Yeah. It's okay? So we're going to practice more this type of actually the problem. Okay? So see you on Wednesday.